Hello APC Mechanics students in Unit 1 Kinematics, Class 9, Calculus Approach, Part 3. Then let's start with Section 1, Rational Function and its Derivatives. The rational function is a function defined by u over v, where u and v are two functions of time such that v is different than 0, because we cannot divide by 0, that would be an undefined function. The derivative of a rational function is given by, so here we're defining or introducing the derivative of a rational function, and that would be u prime v minus u v prime over v square, and that is the derivative of the numerator multiplied by the denominator minus the derivative of the denominator multiplied by the numerator divided by the denominator square. In the operator notation, the derivative of a rational function would be given as follows. Suppose that the potential energy of a physical system is given by the function u is 1 over t, then its derivative, which later will be related to a force, is given by u prime, which is 1 over t prime, and this is given by minus 1 over t square. And let me apply here the formula carefully. So this is a rational function which is given by 1 over t, and that would be u, and that would be v. So in this case, the derivative of u over v is given by u prime v minus u v prime over v square. So if u is 1, which is the numerator, then the derivative is given by 0. And if the denominator is t, then its derivative is given by just simply 1. Now let me plug this in the formula here. Then u prime is 0, so that would be 0 multiplied by t minus u, which is 1, and v prime, which is 1, divided by v square, and v is t, and that would be t square, and that would be minus 1 over t square. Now example 1, for each of the following cases, find the derivative of the given function f. The given functions are well defined. So in math, whenever we introduce irrational functions, we need to discuss whether the function is defined over a specific interval or not, because we know that we cannot divide by 0, but in physics we consider that all functions are well defined. Then let me start with part A. So this is a rational function, then that would, so u is the numerator, which is 1, its derivative is given by 0. The denominator is linear function, the derivative would be a constant, so now we can apply the formula, and that would be given by u prime v, which is 0 multiplied by 2t minus 1, minus u, which is 1 multiplied by v prime, and that would be 2, divided by 2t minus 1 to the power of 2, and that would be negative 2 divided by 2t minus 1 to the power of 2. So that would be the answer for part A. Now for part B, so u would be given by 3t minus 4, a linear function, its derivative is gonna be 3, v is t square, its derivative is gonna be a linear term, which is 2t. So now applying the formula, that would be u prime multiplied by v, which is 3t square, minus u v prime, and that would be 3t minus 4 multiplied by 2t divided by t squared to the power of 2. And no need to expand here, because the objective of this example is just to apply the formula. And now for part C, u, the numerator, is given by 4t, its derivative would be a constant. Now v is given by t square plus 1, its derivative would be 2t. Now we can plug them, so it would be u prime v, which is 4 multiplied by t square plus 1, minus u, which is 4t multiplied by 2t, and divided by t square plus 1 to the power of 2. Now for part D, we need to derive the tangent function. So basically, we haven't introduced previously the derivative of tangent function, but this can be done by realizing that the tangent can be written as a sine t divided by cosine t. So the numerator is sine, then its derivative is a cosine. The denominator is a cosine, then its derivative would be minus sine t. And now we can plug them. So that would be u prime multiplied by v So cosine t multiplied by cosine t, that would be cosine square, minus uv prime. So we have minus with a minus, that would be plus, sine square over v square, which is cosine square t. And here let me simplify a bit, because this is an important derivative. So here we can split the fraction, and this is given by cosine square t over cosine square t plus sine square t over cosine square t. So this is equal to 1 plus tangent square t. So the derivative of a tangent t, also this can be written as 1 over cosine square t, because cosine square plus sine square is always equal to 1, and this will be illustrated later. So we should always remember that the derivative of a tangent function is given 1 by 1 plus tangent square t. And as you can notice that we started with a linear function of tangent of t, which is mean the power of tangent of t is 1, which is linear. And this gave us, when we derive, it gave us a quadratic function, because we are dealing with trigonometric functions, and the way to deal with trigonometric functions is not trivial. Okay? So the derivative of tangent t would be 1 plus tangent square t, after you realize that tangent can be written as a fraction of sine over cosine. Now, section 2, logarithmic function and its derivative. The logarithmic function denoted by f is ln t, defined for t is positive, is a function widely used in physics to linearize the growth decay of other functions. Introducing its derivatives, then ln of t, the derivative of ln of t is 1 over t. Alternatively, in the operator notation, it can be written as follows. More generally, we can define the functional derivative of the logarithmic functions using the chain rule, which is given by ln u. So here we have two functions embedded within each other. We have the ln function, and we have the function which is itself u. So the derivative of ln u would be 1 over u multiplied by the derivative of the inner function, which is u prime, and this can be written as u prime divided by u. So here basically we're using the chain rule, which states that we multiply, after we derive, we multiply by the derivative of the inner function. And here I'm putting a condition where u is a strictly positive function, because as stated here, that the parameter of the ln function should be always positive. No need to worry about domain of definitions in physics, because we assume that all functions are well defined and analytic functions. So suppose that a physical quantity is governed by the following logarithmic function given by f is equal to ln of 2t minus 1. Then the derivative of this function would be what? So ln u, the derivative of ln u would be u prime over u, and in this case u is given by 2t minus 1. Its derivative is given by a constant, so the derivative is given by 2 over 2t minus 1. And this is in the operator notation. For each of the following cases, find the derivative of the given function f. The given functions are well defined. So in this case, that would be u prime over u. This is u, a quadratic function. Then u prime would be a linear, which is given minus 2t over 1 minus t squared. That would be the answer for the first part. For the second part, this is quadratic. Then the derivative would be a linear, which is 4t divided by 2t squared minus 5t. That would be the answer for part B. And for part C, so we have the inner function is said to be an exponential function. So u in this case is given by 2 multiplied by 1 minus e minus 3t, and we need to find the derivative of this function. This is a special function in physics. We'll discuss it later in unit 2, which represents the smooth growth of a certain quantity. So we need to expand it, and this is given by 2 minus 2e minus 3t. Then its derivative in this case is given by what? The derivative of a constant is 0. Minus 2 can be dragged out. And what about e minus 3t? So remember that the derivative of e power u is given by u prime eu. So we derive the inner function, and that would be minus 3 e minus 3t, and that would give us what? 6e minus 3t. And in this case, it is given by 6e minus 3t divided by 2 multiplied by 1 minus e minus 3t. Alright, so let's introduce some identities. Section 3, the exponential and logarithmic functions are introduced in a way such that they are inverse of one another. That is, so the ln, the logarithmic and the exponential functions are inverse of each other, so they cancel. Because here we have ln of e to the power of t, so they cancel, that would be simply t. And the other way around, e to the power of ln t, that would be t, because ln and the exponential would cancel as well. These two identities are crucial and they are implemented whenever we're solving for a logarithmic or exponential equation. So an important thing we do while we're solving or discussing equations, we need to identify the type of the equation. For example, if it's linear equation, quadratic, etc. Why it is important to do so? Because each type of equation referred by a certain name has a specific way of solving. So whenever we're dealing with logarithmic or exponential equation, that means the equation itself includes logarithmic or exponential functions. We need to keep these two identities in mind, as we shall see when we introduce the drag force in Unit 2. Now, section 4, differential equations. Differential equations are a class of equations that include the variable and its derivative. For example, this is a first order differential equation. Why? Because it includes a relation between the position and its derivative, which is x dot. Another example of a differential equation would be x double prime plus omega square x is equal to 0. Omega is a constant. X is the position and x double dot would be the double derivative of the position, and this is known as the acceleration. In fact, these are two perfect examples of dynamical system. That would be, for example, an object falling in the presence of a drag force, and that would be simple harmonic motion. Differential equations are unique physical equations and encode the evolution of the system. For example, kinematic equations are solution of differential equations, and these differential equations are obtained from big laws like Newton's laws and conservation of energy. Basically, here we're just introducing the notion of differential equations. We should able to realize that not all equations are the same. There is a certain class of equations that are called differential equations, and they are given by a relation between the variable itself and its derivative, and such type of equations, they encode the physics of the system. And they are derived from big laws like Newton's laws and the conservation of energy that will be introduced in Unit 2 and 3 respectively. Later on, we're gonna see how to solve these differential equations using a specific method called the separation of variables. And now by that, after we have introduced the derivative of the polynomial, the product, trigonometric, exponential, logarithmic, and rational function, we can complete the following table that includes basically all derivatives of different functions that we're gonna encounter throughout the course. Now, problem 1, a crash test car of mass 1000 kilograms moving at a constant speed of 12 meters per second collides completely inelastically within an object of mass 500 kilograms at a time t is equal to 0. The object is initially at rest. The position x in meters of the car object system after collision is given as a function of time in seconds by the expression. So the position after the collision is given by this one. So basically here what's happening, we have two objects given by the mass 1000 and 500. They're gonna collide, and after the collision or after the accident, they will form a single system given by a total mass of 1000 plus 500, which is 1500 kilograms. So the mass of our system for this position is given by this amount. In part A, we need to determine the expression of the velocity of the car object system after the collision as function of time. And this is straightforward. Why? Because we have the position and the velocity is related to the position independent of the type of motion via calculus. So let's proceed with part A. We know that V is given by dx by dt, which is d by dt of 8 over 5 ln 1 plus 5t Now this is a constant, can be dragged out. That would be 8 over 5 d by dt of ln into 1 plus 5t, and we know that the derivative of a ln function using the chain rule of ln u, that would be u prime over u. So that would be given by 8 over 5 multiplied by the derivative of the linear would be a constant, which is 5, divided by 1 plus 5t. 5 and 5 would cancel, and the velocity of this combined system would be given by 8 over 1 plus 5t. So let me write the answer for the velocity here. So this is given by 8 over 1 plus 5t. Notice that here I didn't put the unit to be meters per second because it is expressed in terms of another parameter. Part B, determine an expression for the resisting force on the car object system after the collision as a function of time t, knowing that it is given by Newton's second law, F is ma. So the restoring force is given by the law of dynamics, which is a Newton's second law, F is ma. We need the mass, we need the acceleration. We're talking about the system which consists of the car and the object. The mass would be given by 1000 plus 500, which is 1500 kg. So we know the mass. Now what about the acceleration? We have the velocity, but we already know that the acceleration is related to the velocity via derivative. So this is given by dv by dt. Then that would be 1500 d by dt of 8 into 1 plus 5t. So let me do the derivative of the rational function here quickly. U is 8, then u prime would be 0. So v is 1 plus 5t. Its derivative is gonna be a constant, which is 5. Then that would be 1500 multiplied by u prime v, that would be 0, minus v prime u, which is 5 multiplied by 8, divided by 1 plus 5t to the power of 2. And multiplying everything, that would be minus 60,000 divided by 1 plus 5t square. And here no need to put any unit which is in newtons because it's expressed in terms of another parameter. And here the minus sign is very crucial because this force is known as a restoring force or resisting force, as we shall see in unit 2. Sorry, it's a resisting force and not a restoring force, alright? Now problem 2, the 100 kg box shown above is being pulled along the x-axis by a student. The box slides across a rough surface and its position x varies with time t according to the equation x 0.5t cubed plus 2t, where x is in meters and t is in seconds. Determine the speed of the box at time t is equal to 0. So basically the speed will be related to the position independent of the type of motion by a derivative. So the answer for part A, that would be v, which is given by, so 3 multiplied by 0.5, that would be, let me write it down, 3 multiplied by 0.5 t square plus 2t, its derivative is given by 2, and that would be 1.5 t square plus 2, but we need the speed at a specific instant, which is t is equal to 0. Then the speed as t is equal to 0 is given by 1.5 multiplied by 0 to the power of 2 plus 2, and that would be 2. Everything is expressed in the SI, x is in meters, t is in seconds, and the answer would be 2 meters per second. Alright? So let me write here in part B that already we have the speed, which is given by 1.5 t square plus 2. No need here to put any unit because it's parameterized by t. Now in part I, they're telling us determine the following as function of time. Idea 1, so Bi, the kinetic energy of the box, given that the kinetic energy is given by half mv squared, this is straightforward. We have the mass, which is 100. We have v as function of time. Then K would be given by half the mass, which is 100, multiplied by 1.5 t square plus 2 to the power of 2, and that would be 50 multiplied by 1.5 t square plus 2 to the power of 2. No need to put any unit because it's parameterized by time, and also no need to expand it. We can keep it in the following compact form. So let me write now that we have that the speed is given by 1.5 t square plus 2, and the kinetic energy would be given by 50 into 1.5 t square plus 2, all of that to the power of 2. Now in idea number 2, the net force acting on the box given that F net is ma, so F net would be the mass, which is 100, multiplied by the acceleration. Now the acceleration is related to the velocity via derivative, and that would be dv by dt. Okay. So 100 multiplied by d by dt of 1.5 t square plus 2, and that would be 100 multiplied by, so the derivative of the constant is 0, quadratic would be linear, which is 3t, and that would be 300t. So no need to put any in it because it's parameterized by time. So idea number 3, the power being delivered to the box, given that the power is the derivative of the kinetic energy with respect to time. The kinetic energy was given by 50 multiplied by 1.5 t square plus 2 to the power of 2. So the power in this case is given by d by dt of this expression, which is 50 into 1.5 t square plus 2, all of that to the power of 2. So we can drag the 50 out. That would be 50 d by dt of 1.5 t square plus 2, all of that to the power of 2. And here we need to be very careful because we're deriving a functional. Two functions here. We have the quadratic function and the power function. So we need to drop down the power. So that would be 2 multiplied by the inner function. We reduce the power by 1, so 2 minus 1, that would be 1. We can keep it like that. And we multiply by the derivative of the inner function, which is given by 3t. Alright, now we can do the following. So 50 multiplied by 2 is 100, times 3 is 300, so that would be 300t multiplied by 1.5 t square plus 2. And here no need to put any in it because it's parameterized as function of time. And finally, the last part for this video, we need to calculate the network done on the box during the interval 0 and 2 seconds, knowing that the network can be calculated using the formula, using the relation network is equal to the variation of the kinetic energy. Delta K stands for K2 minus K1, which is K2 computed at an instant 2, and K1 is computed at an instant 1 such that T2 is greater than T1. T2 would be at 2 seconds and T1 would be at 0 seconds. So let me write again that the kinetic energy is given by 50 into 1.5 t square plus 2 to the power of 2. So the network would be delta K, which is K2 minus K1, and that would be K computed at the instant t is equal to 2 seconds minus K computed at the instant t is equal to 0 seconds. So K for t is equal to 0 seconds is given by what? That would be 50 into 1.5 multiplied by 0 to the power of 2 plus 2. Okay, that would be, if you plug it on the calculator, that would be exactly 200. And let me say that the unit of energy is joules. Either this will be studied in unit 3. And K at t is equal to 2 seconds. We replace time by 2. Plugging this expression on the calculator, we're gonna get a value of 3200 joules. And now we're ready to calculate the network, which is basically this minus that. That would be 3200 minus 200, and the answer would be 3000 joules. Then that's it for me in this video, guys. See you soon in a new one.